6:10 here in my watch. Okay. So maybe we can now start. Okay. Let me just share my slides. Okay. I am now sharing my slides. Okay. So I hope everyone can see them, and I hope everyone can hear me as well. Okay. Mm. So again, if you have any concerns, just try to call my attention anytime. And yeah, you can also try to chat in the chat box now if you have any concerns at all. Now, please interrupt me anytime. Okay. So for tonight, let's try to discuss the basics, no, of the shear strength of a soil. Okay. Any soil for that matter. Okay. So the shear strength of a soil mass, okay, is defined, okay, as the internal resistance per unit area that the soil mass can offer to resist failure, okay, and sliding along any plane inside it. Okay, so one must understand the nature of the shearing resistance in order to analyze slope stability problems, such as soil stability problems, such as bearing capacities, soil bearing capacities. Okay, this is the when you say the bearing capacity, this is the capacity of the soil to resist a load. Okay, may it be a dead load or a live load or an earthquake load. Okay, yeah. So this the bearing capacity. Okay, as well as slope stability and lateral pressure. Okay, lateral earth pressure on earth retaining structures, no, which will be our last. Lateral pressure will be our last topic. Okay. Um, Now I just recalled I think the other day I think a an earthquake occurred in Davao, if you have heard of that. Okay, I think the earthquake magnitude is around 7.2, I think. Yeah. Normally liquefaction, for example, can occur with with earthquake magnitudes around 7. Okay. Yeah. Then I saw, I think there was a post, a post that I saw wherein the house seemed to have collapsed. Okay, in Davao. Okay, it's quite sad to see because it seems to be a quite brand new house. But yeah, the it seems that the first floor failed. No? Okay, and then the entire second floor was, yeah, down, and it even hit the cars, the owner's car. No? Okay, it's quite sad to see. Okay, so I hope that yeah, in the future we can try to avoid this happening from structures. Okay. Yeah. So again, in the geotechnical reports that they prepare, for example, we aside from the bearing capacity that we put in the report, we also indicate there the lateral earth pressure coefficients. Okay, for the design of retaining structures, earth retaining structures, as well as the settlement analysis, wherein we include also, aside from the static settlements, such as the immediate and the consolidation settlements, which we discussed last time. Okay, we also include in the geotechnical report the liquefaction settlements that can be generated by a certain earthquake magnitude. Okay, so we also put that in the report as a reference by structural engineers. Okay, so normally in the geotechnical reports, we also try to identify problematic soils, okay, such as collapsible soils, swelling soils, okay, as well as liquefiable soils. No? And it all depends on the shear strength of the soil. Okay, so that's why it's very important to understand the shear strength of a soil. No? May it be sand or may it be clay, for example. No? Okay, which or in they differ in their shear strength parameters. Okay, so let's try to discuss these shear strength parameters no, that we normally consider in any geotechnical analysis. Okay. Okay, so a certain guy named Moore in the 1900s presented a theory for rupture in materials that contended that a material fails because of a critical combination of normal stress and shearing stress, and not from either maximum normal or shear stress alone. Okay, that's the functional relationship between normal stress and shear stress on a failure plane can be expressed according to this guy. Okay, can be expressed in this equation here, equation 12.1 in your book. Okay, wherein we now have tau sub f is equal to a function of sigma, no? Where tau sub f is the shear stress at failure. Okay, this is the point where your soil fails. Okay, may it be a bearing failure or a slope failure, for example. So that's the shear stress at failure is equal to a function, a certain function of the normal stress. Okay, this is your sigma, no? The normal stress. Okay, so we will define shear stress and normal stress in a while. No? I guess for the basic definitions of normal stress and shear stress, I think we are already familiar with that when we discuss strength of materials. Okay, subject. I think that's our favorite subject no? In civil engineering. Okay. There we define the normal stress and shear stress, wherein the normal stress is you have the force over the area perpendicular to the force. Okay? While the shear stress is equal to the force over the area parallel to the force. Okay, so that's shear stress. Okay, so that's force over area. Now, the same concept we apply here in geotechnical engineering. Okay, so the same definitions for normal stress and shear stress. Okay, so then we consider the normal stress with respect to the failure plane, and then the shear stress with respect to the failure plane. Now, the failure envelope defined by the equation which we have just seen earlier is basically a curved line. Okay. Now, for most soil mechanics problems, it is sufficient to approximate the shear stress on the failure plane okay, as a linear function of the normal stress, no? According to this guy, Coulomb. Okay. So this linear function can be written as shown in this equation here, 12.2 in your book. Okay. So again, don't worry with all this, with all my slides, because all of this can be found in your book. No? Okay. If you want to recall later. So again, this linear function, okay, is given us the shear stress at failure, or the shear strength. No, we now have the shear strength at failure. Okay, that's tau. Okay, is now equal to C, where C is the cohesion. Okay, and then plus sigma, where sigma is the normal stress on the failure plane, multiplied by the tangent of the angle of internal friction. Okay, wherein this cohesion and the angle of internal friction are what we call the shear strength parameters. Okay, so in everything that we do in geotechnical engineering, we always try to determine the cohesion value and the friction angle value for any type of soil and for any relative density as well as consistency of the source. Okay. So equation 12.2 is now what we call, or popularly called as the Moore-Coulomb failure criterion. No? So if you try to research on literatures, okay, so we normally have the Moore-Coulomb failure criterion for soils. Okay. Now, in the case of rocks, then we also have the Hook-Brown failure criterion. Thanks to these guys, Moore, Coulomb, Hoek, and Brown. Okay, so these are the researchers who was able to determine the shear strength parameters for both soil and rocks. Okay, but for the moment, let's just focus on this Moore column failure criterion for soils. Okay? Now, in the case of a saturated soil, okay, so again, I'm talking about saturated soil because the behavior is different when we deal with unsaturated soils. Okay, so again, these are so when you say saturated soils, these are soils below the groundwater level, because again, the behavior of a soil is different when it is above the groundwater level, or we call them partially saturated soils or unsaturated soils, because of the presence of what we call the matrix suction. Okay, but okay, we discussed that in the masteral level. Okay. Now, in the case of a saturated soil, okay, so let's presume that below the ground, if you have a house, okay, so for example, the foundations in your house has an embedment depth of say around 1.5 meters. Okay, wherein you put there the isolated footings. Okay, normally in the houses we have isolated footings or combined footings. Okay, so let's assume that below those footings, immediately you have the groundwater table. Everything's already saturated. Okay, so in that case, then the total normal stress, symbolized by sigma, at a point, or at a particular point, is the sum of the effective stress, which we have defined previously. Uh, Okay, so that's sigma prime. Okay, the sigma prime and the pore water pressure U. Okay, um, in this case, now wherein you have a saturated soil. Okay, so in the case of an unsaturated soil, if you still want to know more, then we have both the pore water pressure as well as the pore air pressure. Okay. So for the moment, let's stick to this equation. Okay. So here in this formula, the effective stress, no, sigma prime, is carried by the soil solids. Okay. So, which means that the more column failure criterion expressed in terms of effective stress, okay, will be in this form on equation 12.3 in your book, no? Wherein the shear strength at failure, okay, when the soil fails, no? Okay, thus the shear strength at failure is now equal to C prime plus sigma prime times the tangent of phi prime, okay, where phi is your angle of internal friction, no? Or the friction angle, okay? And these are based on effective stresses, okay, not total stresses. So when we talk of equation 12.2 in your book, that's total stresses, okay? And then equation 12.3 is effective stresses. No? That means that the loads, when you say effective stresses, the loads are purely carried by the soil solids. No? Whereas if we have total stresses, then the loads are carried by both the soil solids as well as the poor water. Okay? Yeah. In practice, we always prefer um, the effective stress, no? Shear strength parameters. Okay, depending on the ground conditions. If you have either drained conditions where water can easily flow, or undrained conditions, no? Or water cannot easily flow, or when the load is applied relatively fast in comparison to the drainage of the water below the ground or into the source, okay, in such a way that it can be considered as total stresses, no? Okay, or undrained conditions. Okay. Okay, so here we see the Moore-Colomb failure criterion. We're in here in figure A. You have here a soil sample. Okay, if you can see my cursor, you have here a soil sample wherein you have here, for example, your failure plane. Okay, the failure plane AB. Okay, and then here you have the corresponding normal and shear stresses being applied into the soil sample on the sides. Okay. So with respect to the failure plane, AB, okay. So we now have here the effective normal stress. That's a sigma prime. Okay. So that's normal. No? So that's the normal force perpendicular to the failure plane AB. Okay. And then we also have your shear stress tau. Okay. Wherein you now have the shear force parallel to the failure plane AB. No? If you're seeing my cursor, the failure plane AB. Okay. So if we plot the effective normal stress, okay, the sigma prime against the shear stress at tau, okay, then we now have here the failure criteria, no? Okay, so we can generate here the Moore-Colomb failure criteria. Okay, this is this line, this blue line here. Okay, yeah, in such a way that this blue line here, depending on the behavior in the soil, okay, this blue line may either be flat or it may be inclined. Okay, in this case, you have an inclined failure criteria, okay, in such a way that it has a friction angle. Okay, so the slope of this line is now what we call the friction angle. Okay, since here we have an effective normal stress, sigma prime. So here we have your effective friction angle. Okay, and then the intercept wherein this line is having with respect to the shear stress uh, coordinate. Okay, then this is now what you call your effective cohesion. Okay, so this is more or less a slope intercept form. No? If you still recall your um, uh, think basic geometry, I think, no? Okay, or trigonometry, no? Okay, you have the slope intercept form. Okay, or your basic mathematics. Okay, so this is now your slope. Okay, and then this is now your intercept. Okay, the slope intercept form. Okay, so this is now your line. Okay, so for the rest of the slides, we will now be determining this shear strength parameters, which is the friction angle and the cohesion. Okay, whether it is a total shear strength parameters or effective shear strength parameters, depending if we have drained or undrained conditions. Okay, so I hope by now uh, it is quite clear with you the difference between drained and undrained conditions. Okay. So again, when we say drain conditions, that means the load is slowly applied to the sample in such a way that only the soil solids is resisting the load. Okay. But when we say undrained conditions, that means the load is applied quite fast. Okay, in such a way that it didn't have time for the water to flow in such a way that both the soil solids and the pore water are both resisting the loads. Okay, so in that case, it will become total stress behavior. Okay, while if there is a drain condition, then it will behave as an effective stress behavior. Okay. Okay. The two equations that we have seen so far are the expressions for the shear strength based on total and effective stresses, respectively. Okay. Now, here we just have some typical values, no? Okay. Commonly found in the field. Okay. So here there's some generalizations. Okay. Generalizations that the value of the effective cohesion, okay, the effective cohesion, that's C prime, for the case of sands and inorganic silts is zero, for example, wherein sands and inorganic silts, I think by now, hopefully you are already familiar how to classify them based on the USCS classification system or the Unified Soil Classification System. Okay. Now, in the case of a normally consolidated clays, okay, so I think last time we just discussed um, the difference between normally consolidated clays and over consolidation or over consolidated clays, depending on the over consolidation ratio. Okay, so that's why it's important to understand between the difference between normally consolidated and over consolidated clays, because with respect to the shear strength parameters, they can be quite different. Okay, okay, theoretically. Okay, so in the case of a normally consolidated clays, the effective cohesion can be approximated as zero. Okay, for over-consolidated clays, then it can have an effective cohesion greater than zero. Okay, yeah. So that's some of the differences between a normally consolidated clay and over-consolidated clay. Okay, so the effective friction angle, on the other hand, is that's a phi prime. Okay, that's effective friction angle is sometimes referred to as the drain angle of friction. Okay. Now, here in table 12.1 in your book, you have here some typical values for the effective friction angle for some granular soils. Okay. So when you say granular soils, okay, this can be gravels or sands and silts. Okay. They can um, be granular soils. Okay. So here you have the different effective friction angles um, depending on the structure of the sand. May it be rounded grains or angular grains. No? Normally, we have rounded grains when these are um, when these sands, for example, are generated by river alluvials. No? Okay, a river alluvial source. Okay, uh, if you notice, no, kanang makakita tag mga bato sa river, no, nahimo na tag mga lugod, no. Okay, sa Bisaya pa himo na mga lugod. Okay, so these are actually examples of rounded grains, no, because these are being polished by the flow of the river, no. Okay, so these are rounded grains. No? So in that case, you can have different effective friction angles, whether you have a loose sand, a medium dense sand, or a dense sand. Okay. Now, these are again the relative densities. Okay, that we can find for granular soils, which we sometimes determine during the geotechnical investigation, no? With respect to the field values. Okay, so we can determine them. Okay. Now, aside from rounded grains, you have also angular grains. Okay. Now, for angular grains, you notice here that the shear strength parameters, no, okay, for angular grains is larger or higher than the rounded grains. Okay, because between angular grains and rounding grains, you can have a better friction there. Okay. So examples of angular grains is when you have crushed rock, for example. No? Okay, for those of you here who have a construction business, then sometimes we buy crushed rock material. Okay, so these are examples of angular grains. Okay, yeah. And then you also have here a gravel with some sand. Okay, so it has quite a high friction angle. Okay, and then you also have here some silts. Okay, with a lower friction angle, no? Effective friction angle. Okay, so this just gives you an idea, no, of the drained friction angles for sands and silts, or as well as gravels. So later we will be discussing some laboratory tests, okay, on how that can be used to determine these parameters. Or in practice, we can also use empirical equations, established empirical formulas that we can use depending on the field values to determine the shear strength parameters. Okay, because it's not all the time that we can do laboratory tests. Okay. Okay. So, as stated in the Moore-Coulomb failure criterion, okay, the failure from shear will occur when the shear stress, okay, on a plane reaches a given value as given by this equation here. Okay. Yeah. So when you have this equation now, then that means you now have failure. Okay. So to determine the inclination of the failure plane, with respect to the major principal plane, okay, we can refer to this figure here. Okay, yeah. So, for example, you now have here the failure plane. Okay, the failure plane EF. Okay, so this failure plane will now create an angle of, let's say, theta. Okay, with respect to the major principal axis. Okay, Um, here we have, let's say, sigma sub 1 prime, okay, and sigma sub 3 prime. Okay, let's call them sigma sub 1 and sigma sub 3. Okay, so sigma sub 1 prime is now what you call your principal, um, uh, your major. No, we call this your major principal stress. Okay, so if this is the major principal stress, then sigma sub 3 prime is now what we call the minor principal stress. Okay. So if this is now the major principal stress, okay, along the direction, no, because it is along the direction of the load, okay, where we apply the load, okay, for example, the load from your house, for example. So it's the major principal stress, okay. So if it is the major principal stress, then the area, okay, this line DC, no, or the line DC perpendicular to the major principal stress is now what we call the major principal plane. Okay? So the minor principal stress, sigma sub 3 prime, okay, then that is also correspondent to the minor principal plane AD perpendicular to the minor principal stress. Okay. So then we now want to determine the angle of inclination. Okay. The angle of inclination theta. Okay. Theta with respect to the major principal plane. Okay. So to do that, let's try to consider here in this figure 12.3 in your book. Okay. So please try not to get lost. If you have your book, you can try to find this figure there. Hopefully it's still consistent. Okay. So you have here the Moore circle. Okay. The Moore circle, we call it the Moore circle. So I think we have discussed Moore circles in strength of materials. Okay. So you have here the Moore circle, and then you have here the failure envelope. Okay, we call this the failure envelope due to the failure criteria, the Moore column failure criteria. Okay, um, wherein this failure envelope can be generated once we now have uh, the failure in the soil, no? Created by these failure planes. Okay. So here in if you plot now the effective normal stresses, sigma that's phi prime. Sorry, so sig let's the sigma, not sigma prime. Okay, sigma prime. Okay, um, with respect to the shear stress. Okay, then we can plot here the more circle. Okay, wherein one point of the Moore circle here is your sigma sub 1 prime, or the major principal stress, no? The major principal stress, okay, sigma sub 1 prime. And then this one here, the other point of your Moore circle is your minor principal stress, no? That's sigma sub 3 prime, okay? And then here, with respect to the failure envelope, okay, passing through the shear stress ordinate, okay. Then we now have your um, okay, intercept, which is now your C prime, and then this failure envelope has an angle of phi prime. Okay. Now, with respect to the Moore circle, okay, this failure envelope will be acting as tangent. No? Okay, it will have a tangent point to the Moore circle. Okay, wherein if we now try to create a line from the center, okay, this point A, from the center of the Moore circle, okay, and then we project a line from the center to the tangent point of the failure envelope. then we can now call this our 2, let's call this now 2 theta. Okay, 2 theta. Okay, I think we learned that somewhere. We're in, if this is now um, the angle, no, for this um, part of the circle here. No, we have that as 2 theta. Okay, okay. So, um, so here, the radial line AB, okay, the radial line AB would define the major principal plane CD. So where is that? No? So the radial line AB, okay, okay, the radial line AB, okay, will be the same as your major principal plane CD. Okay, so the major principal plane CD is equivalent to your line AB. Okay, whereas the line AD here, okay, the line AD, is that correct? Okay, the radial line AD will define the failure plane EF. Okay, so this radial line AD will define your failure plane EF. Okay? So if we want to determine this theta now, okay, so this theta is just the same as this yeah, 2 theta here, but we know from geometry that 2 theta is equivalent to, okay, equivalent to 90 degrees. Okay, this is 90 degrees plus, okay, from the vertical, no? Okay, I hope you can imagine if you're seeing my cursor. So if we put a vertical line here, that's 90 degrees. Then from this line to this radial line AB, okay, so that angle, okay, that angle is roughly the same as this angle here, no? This effective friction angle, phi prime, okay? In such a way that 2 theta is now equal to, okay? So 2 theta is now equal to 90 degrees plus phi prime, or the effective friction angle, okay? So then if you want to determine theta, okay, then we just simply divide everything by 2. So then theta now is equal to 45 degrees plus phi prime over 2, no? Where phi prime is your effective friction angle. Okay, so that means if we have some idea, if you have some idea of the friction angle of a certain soil material, then we can roughly have some idea of the angle, no, of the failure plane. Okay, where it would fail. Okay. Okay. So there are several laboratory methods available to determine the shear strength parameters, either total shear strength parameters, the C phi, or the effective shear strength parameters, the C prime and phi prime, for various soil specimens. No? Okay. Now, these are enumerated here. We have the direct shear test, the triaxial test, the direct simple shear test, the plane strain triaxial test, and the torsional ring shear test. Okay. I think the last three are normally used for research purposes, but the first two here, the direct shear test and the triaxial test, are the ones that is most commonly used um, in the academe, or in teaching work, okay, for laboratory exercises, as well as in actual practice. Okay, in actual practice, we normally specify direct shear test and triaxial test, depending on the sample that can be extracted, no, from the geotechnical investigation. Okay, and then we have them brought into the laboratory. Okay. So, um, okay, so let's first discuss the direct shear test. Okay, and then later on let's discuss the triaxial test. So the direct shear test, okay, is yeah, the oldest. No? Okay, it can be considered as the oldest and the simplest form of the shear test arrangement. Okay, so here you have a test equipment which consists of a metal shear box, okay, in which the soil specimen is being placed. Okay, and then the soil specimens here may be square or circular in plan. Okay, and then the size of the specimens generally used is about 51 by 51 millimeters or by 102 by 102 millimeters across and about 25 millimeter high. Okay, and then the box is split horizontally into halves. Okay, so here we have a schematic diagram of that direct shear test equipment. Okay, so here, for example, this is your soil sample. Okay, yeah. And then if you're seeing my cursor, this one here is we call it the porous stone. Okay, that will confine the sample. Okay, and then this one here, okay, on the sides is your shear box. We call it the shear box. Okay, and then during the test, we apply both the normal force. Okay, we apply the load here, the normal force. Okay, as well as we apply a load here, which is now the shear force. Okay. Now, in the direct shear test, normally we already predict the failure plane, no? Which is somewhere along this line, a horizontal line, because you try to split the shear box, no, into halves, okay, by applying both normal and shear forces. Okay, so here we have an example of a direct shear test equipment. Okay, wherein this one here you apply the normal force. Okay, so you can imagine here you have your sample. Okay, you have your sample. Okay, so this one here, say, so in that figure we are looking at the plan view. No? So we are looking in this direction. Okay, so you have here your sample. Okay, so this one you apply the normal force to create a normal stress. Okay, and then this one here you apply the shear force. Okay, to create to create the shear stress. Okay, and then this shear force, okay, is being created by this proving ring. No? Okay, measured by this proving ring here. We call the proving ring. Okay, okay, okay. Now, depending on the equipment, okay, the shear test can be either stress controlled or strain controlled. Okay. Now, in stress controlled tests, the shear force is applied in equal increments, okay, until the specimen fails. Okay. Now, the failure occurs along the plane of split of the shear box. Okay, so this one here, okay, along the plane of split. Okay. Now, after the application of each incremental load, the shear displacement of the top half of the box is measured by a horizontal dial gauge. I think that's this one. Okay, horizontal dial gauge. Okay, and then the change in the height of the specimen uh, during the test can be obtained from the readings of the dial gauge, no? That measures the vertical movement of the upper loading plate. Okay? So with that, since we know the area and then you know the change in the height, okay, then we can also determine the volume change in the soil specimen. Okay? Now, in strain control tests, a constant rate of shear displacement is applied to one half of the box by a motor that acts through gears. Okay. Then the constant rate of shear displacement is measured by a horizontal dial gauge. Okay. So the resisting shear force of the soil corresponding to any shear displacement can be measured by this horizontal proving ring, or if you don't use a proving ring, you also have a load cell. Okay, a load cell. Okay, when I was still doing my research in Japan, we did not use a proving ring, but we used a load cell. Okay, later on I'll show a picture of that. Okay, but that was testing for unsaturated soils. Okay, so we have a triaxial test specific only for saturated soils, and we have a triaxial test equipment is specific for unsaturated soils, which I will show later. Okay. Okay. Uh, okay. So here we have a typical or a typical plot. Okay. For the shear stress, no, derived in a with a direct shear test equipment. Okay. For example, here, if you look at this figure, okay, you look at this figure. So we now have here two plots. Okay, two plots. One is for a dense sand. If you're seeing my cursor, one is for a dense sand condition, and another one is for a loose sand condition. Okay. So here we plot the shear stress in the ordinate axis, and then here we plot the shear displacement, no? Okay, in the horizontal axis, okay, which you can measure from the direct shear test equipment, okay, because of this dial gauges, okay. Oh, okay, so there in this figure, okay, so we have based on this results, okay, so we have here uh, some observations, okay, so there we see in that result that in the case of loose sand, okay, loose sand, okay, for example, now when you say loose sand, for example, during compaction works, when you still backfill the material, okay, that is still loose, okay, in loose condition. But when you already compact it, then that's already in dense condition. Okay. Now, in the case of a loose sand, okay, then the resisting shear stress increases with shear displacement until a failure shear stress of sigma, or sorry, tau sub f is reached. Okay. And then after that, the shear resistance remains approximately constant for any further increase in the shear displacement. So if we look at the graph here, so in the case of a loose sand, okay, so the resisting shear stress increases. Okay, if you're seeing my cursor, it increases with respect to shear displacement um, until such time that it will become or the so this is now this part here, no? This is now what you call your failure, no? Your failure shear stress. Okay, so at this point, okay, your soil already failed. Okay, and after that, as the shear displacement continues, so as the soil material continues to displace, then the resisting shear stress will just be constant. No? Okay, okay. And so we now call that the ultimate, no, the ultimate shear strength. Okay. Now, in the case of a dense sand, okay, the resisting shear stress, okay, so this is just observation. The resisting shear stress increases with shear displacement, okay, of the soil sample until it reaches a failure stress. No, that's tau sub. Okay, that's the shear strength at failure, okay, which we now call as the peak shear strength. Okay. Now, after the failure stress is attained, then the resisting shear stress gradually decreases as shear displacement increases until it finally reaches a constant value, which we now call as the ultimate shear strength. Okay, so again, if you look at the figure here, if you look at the dashed line, okay, so for the case of a dense sand, okay, then the resisting shear stress, okay, increases, okay, as the shear displacement increases until such time that here your sample already failed. Okay, it will fail. Okay, and then at this point, this is now your peak. We now call this your peak shear strength. Okay, that's a tau sub f. And then after the sample has already failed, then the resisting shear stress will now decrease with increasing, with continuous increasing shear displacement. Okay, and then until it reaches what we call as the ultimate, shear strength, in the case of dense sand. No? So they will be reaching here at the same point, to determine the ultimate shear strength. Okay. So normally in practice, we are more interested with the ultimate shear strength, okay, of the material. Okay. Now, with respect to the change in the height of the specimen, okay, if you consider here this line as the zero, for example, in such a way that below this line is the soil will compress, okay, and then above this line, that means the soil will expand. Okay, yeah. So in the case of a loose sand, okay, so as the shear displacement increases, then yeah, the the soil sample will be in a continuous compression mode. Okay, so it is continuously compressing. Okay, but in the case of a dense sand, as the shear displacement increases, initially it will compress, okay, but eventually the dense sand will expand. Okay, yeah, it will expand. Okay, so this is now the variation in the change of the height of the soil specimen during the conduct of a direct shear test, or direct shear test, no? Using such direct shear test equipment. Okay. So please take note of these strengths, no? The peak shear strength and the ultimate shear strength. Okay. So here we have some typical results for the shear strength parameters in the case of a dry sand. Okay, using a direct shear test. Okay, so here we plot the effective normal stress with respect to the shear stress. Okay, that's sigma prime and tau. Okay, so here we have the different plots for this phi prime, which is now your peak shear strength parameters. Okay, and then here with these plots, then you can now determine your ultimate shear strength parameter, no? Effective ultimate shear strength parameter. So again, the ultimate shear strength parameter is lower than the peak shear strength parameter. No? So that's why here the peak shear strength friction angle is higher than the ultimate shear strength friction angle. But in geotechnical analysis, we are more interested with this one, no? The ultimate shear strength parameter. Okay. Okay. Uh, Now, in the direct shear test arrangement, the shear box that contains the soil specimen is generally kept inside a container that can be filled with water to saturate the specimen. Okay. Now, in a direct shear test, we can perform what we call as a drain test, which is done on a saturated soil specimen by keeping the rate of the loading. Okay, that's the application of the load. Okay, so that's this one here. No? The application of this load. Okay, so that the rate of loading is low enough so that the excess pore water pressure generated in the soil is dissipated completely by drainage. Okay, so that means the soil specimen is undergoing consolidation. Okay, so I think last time we were discussing consolidation settlement. Okay, so the pore water from the specimen will then be drained through the two porous stones above and below the soil specimen. Okay, so I think you have that figure in your book. Okay, you can just look at that. Okay. Now, because of the hydraulic conductivity of sand, okay, which is quite high, the excess pore water pressure generated due to the loadings with respect to both the normal and the shear forces, okay, is dissipated quickly. Okay, hence, for an ordinary loading rate, we can say that in the drain test for a direct shear test equipment, then essentially full drainage conditions exist. Okay. So the friction angle phi prime obtained from a drained direct shear test of a, take note, that's a saturated sand. Okay, will be the same as that for a similar specimen of a dry sand. Okay, so it's irrelevant if it is saturated or dry sand. In the case of a drain direct shear test, okay, because you will have because of the dissipation of the excess pore water pressure, then you will have if effective stresses. No? Okay, so only the soil solids will carry the load. Okay? Now that is with respect to sand. Okay. Now in the case of clays, the hydraulic conductivity of clay is very small compared with that of sand. Okay, I think we have discussed the topic on seepage earlier, where we tried to compare the hydraulic conductivities or the permeabilities of both sand and clay. Okay. So when a normal load is applied to a clay soil specimen, a sufficient length of time must elapse for full consolidation, or that is for the dissipation of the excess pore water pressure. Okay? For this reason, the shearing load must be applied very slowly. Okay, so that's why if you want to do a drain direct shear test, in the case of a clay samples, then the test may last from 2 to 5 days. Okay, in order for you to have some results. Okay, so it takes some time. Okay, so just imagine if you are to test three samples. Okay, for you to plot. Okay, for example, here these are actually 1, 2, 3, 4, 5. These are actually 5 tested samples. Okay, so just imagine if that is a clay material. Okay, so each test would take around say 5 days. So that means in order for you to get this plot, in the case of clay, then you will have to wait for 1 month. Okay, around 1 month. Okay, no, no, around, yeah, that's uh, yeah, that's about 1 month and 1 week if you only work from Monday to Friday. Okay. So it will take you 1 month and 1 week just to have this plot here. Okay. 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 So here we have some results. Okay. Typical results for a direct shear test on an over consolidated clay. Okay. Um, so here we plot the shear stress with respect to the ratio of the horizontal deformation. Okay. With respect to the dimension of the specimen in the direction of the shear force, that's in percentage. Okay. So here we see that the shear stress or the resisting shear stress in the soil sample increases, okay, until it reaches peak shear strength, wherein the soil sample will start to fail. Okay. And then after that, okay, then the resisting shear stress will start to decrease, no? After the soil sample has already failed. And then it will reach a certain constant value, which we now call as the residual shear strength. Okay. For example, if you have um, clay which failed after a slow failure, okay, then that clay will now have a residual shear strength. Okay, it's no longer the peak shear strength. So, in a slope, for example, if you have clay, before the slope fails, then you have the peak shear strength, okay, of the soil sample. But after the slope failure, then the soil sample will now have the residual shear strength. Okay, yeah. So then when we try to rehabilitate the slope, okay, for example, we apply an MSA wall approach wherein we combine geosynthetics with soil compaction. Then from the residual shear strength, it might go back to its peak shear strength, no? For example. Okay, so so having some of these tests, no? Okay, yeah. Then we can try to plot uh, the results here with respect to the effective normal stress as with respect to the shear stress at failure. Okay. So here to generate one failure envelope, then in this case about say 1, 2, 3, 4, 5, about 5 tests has been done. So that means you have about 5 tests of this. Okay, and then plot it here. Then you can probably generate the failure envelope. Okay. So we have here 3 graphs. Okay. This graph here is the case for an over consolidated clay. Okay. In such a way that here you have your C prime, which is not zero. Okay. So this is now your effective cohesion. Okay. But in the case of the normally consolidated clays, okay, then here your C prime is zero. Okay. So that means the failure envelope only has this equation here. Okay. As compared to the over consolidated clay. Okay. And so this is now the peak shear strength for over consolidated clay. Well, this is the peer shear strength, peak shear strength parameter for the normally consolidated clays. And then this failure envelope here, the failure envelope. Okay. So this is now the plot for the residual strengths. Okay, residual strength. So in this case, we now call this the um, phi sub r prime. Okay, that means it's due to the residual. Okay, the residual shear strength. Okay, so again, the residual shear strength parameter is smaller than the peak shear strength parameter, no? With respect to the clay, no? Obtained from drained direct shear tests. Okay, so so far we have discussed the direct shear test. So now let us discuss about the triaxial shear test. Okay. Now, the triaxial shear test is one of the most reliable methods available for determining the shear strength parameters. Now, because here we don't dictate the failure plane, okay, in the sample. Okay, unlike here in the direct shear test, wherein we force the sample to fail in this direction. Okay, and so there will be stress concentrations. Okay, so that's why the direct shear test, sorry, the triaxial shear test is more reliable because we don't dictate the failure plane, no, in the soil sample. So that's why in research purposes and in conventional testing, it is more widely used. Okay. Um, so here we have so we have here a diagram of a triaxial test equipment, wherein here you have your soil sample. Okay, and then this one here is your porous stone. Okay, porous disc. Okay, and then here you have water. No? Okay, water surrounding the specimen, wherein this water will create a confining pressure. Okay, we call it a confining pressure, which is now equivalent to your sigma sub 3. Okay, earlier we discussed about, or we mentioned sigma sub 1, which is the normal stress, and then um, your major principal stress, and then sigma sub 3 is your minor principal stress. Okay, so the minor principal stress, or sigma sub 3, is equivalent to the confining pressure generated by the water surrounding the soil specimen in a triaxial test. Okay, whereas here the axial load will now create your sigma sub 1, okay, which is now your major principal stress. Okay, so so the confining pressure here can be measured by a cell pressure control. Okay, a cell pressure control, no? Or this confining pressure is also what you call the cell pressure. Okay, so here you have your pressure gauge for the cell pressure control. Okay, yeah. Then here you can have the connections for your drainage or for the pore pressure measurement. No, wherein you can measure the in the case of a saturated soil sample, you can measure the pore water pressure. Okay, but in the case of an unsaturated soil sample, then we can also measure both the pore water pressure and the pore air pressure. Okay. Okay. So in the triaxial test, Okay, the soil specimen is usually about 36 millimeters in diameter and about 76 millimeters long. Okay, yeah. And then the specimen is encased by a thin rubber membrane. Okay, and then placed inside a plastic cylindrical chamber that is usually filled with water or glycerin. Okay, and then the specimen is subjected to a confining pressure by the compression of the fluid in the chamber. So this one, huh? Okay, this fluid here. Okay. So to cause shear failure in the specimen, one needs to apply the axial stress, which we also sometimes call the deviator stress. Okay, later on, we'll define that. Okay, by formula through a vertical loading ram. Okay, so this can be applied in two ways. One can be the application of dead weights or hydraulic pressure in equal increments until the specimen fails, or the application of axial deformation at a constant rate by means of a geared or hydraulic loading press. Okay, so item two here is now what we call as strain controlled test, whereas item one is stress controlled test. Okay. Okay. So you have here a picture, okay, of an ongoing triaxial test. Okay. Mm, Here for this triaxial test, okay, um, um, here they have used a proving ring. Okay, a proving ring for the application of the load. Okay, wherein here you see the soil sample. Okay, being encapsulated by a rubber membrane. Okay, then this can be surrounded by water. Okay, so here you have a clearer picture. Okay, which I took in Japan. Okay, when we also did some triaxial tests. Okay, so here you see the soil sample, okay, being encapsulated by a rubber membrane. Then here you see um, the water, no? That will generate some confining pressure to the soil sample. Okay. Um, if you notice here, I think the difference with that would be here, the chamber is fully filled with water, and then here the sample is fully saturated. Whereas here, the sample is not fully saturated, and then the chamber is also not fully filled with water, because this is to create here. This is only creating a poor water pressure increase in the sample, okay, wherein we can measure the pore water pressure. But here you notice that you have here two pressure gauges. Okay, one pressure gauge here actually measures the pore water pressure, while the other pressure gauge measures the pore air pressure. Okay, yeah. So this was um, just fabricated. No? This equipment was just fabricated in my university in Japan, no? Because they have there the mechanical engineering department in Kagoshima University, and so they fabricate their own equipments for research purposes. Okay, so they don't usually buy commercially, although now you can buy these equipments commercially. Okay, but in Japan, they would prefer to create their own equipments for research. Okay. Okay. Now, by the way, here the the actual deformation. Okay, can be measured by a either by a proving ring or by a load cell. No? In this case, we use a load cell. Okay. Now, connections to measure drainage into or out of the specimen, or to measure the pressure in the poor water, is also being provided in the triaxial test equipment. Okay, such as this one here. Okay, so this connection here for the drainage and this one for the pore water pressure measurement. Okay. Um, with that, then we have now three standard types of triaxial test. Okay. The first one is what we call the consolidated drain test or the drain test. Okay. Which is in abbreviation, that's the CD test. And then we also have the consolidated undrained test or the CU test, normally with poor pressure measurement, okay, poor water pressure measurement. And then you also have the unconsolidated undrained test or the just simply the undrained test, no, or the UU test. Okay. So in the next slides, we will be doing the general procedures, or we'll be explaining the general procedures and implications for each of these three tests. Okay, in saturated soils. Okay, in for the moment, let's talk about saturated soils. Okay, so this one here. Let's talk about saturated soils because this one is an unsaturated soil. Okay. Okay. Now, the first one is the consolidated drain triaxial test, or in simply the CD test. In practice, we call this the CD test. The saturated specimen in this test is first subjected to an all-around confining pressure. That's your sigma sub 3. So that's this one, huh? The all-around confining pressure, okay, in the chamber. And then as confining pressure is being applied, the pore water pressure of the specimen would increase by U sub C. Okay, U means pressure, pore water pressure. C means confining. Okay, confining pressure. Okay. Um, now, um, now this increase in the pore water pressure can be expressed as a non-dimensional parameter, which is now your B. Okay, we call it the Skemptons. Now, Skemptons B pore pressure parameter, wherein the B pore pressure parameter is equal to the pore water pressure increase due to the confining pressure in the chamber. Okay, so that's the pore water pressure increase in the soil sample due to the confining pressure. Okay, here in the chamber, okay, either by water or by glycerine. Divide that by the confining pressure, no, which is your sigma sub 3. Okay. Yeah. Now, if the connection of drainage is now open, okay, so that means here you now open the drainage, no, for water to flow from the soil specimen. Okay. Now, then the dissipation of the excess pore water pressure and thus consolidation will occur. Okay. Then with time, okay, the pore water pressure increase will become zero. Okay. Now, in a saturated soil, the change in the volume of the specimen that takes place during consolidation can be obtained by measuring the volume of the pore water drain. So you have a figure of this in your book. Okay. Now that part is what you call your consolidation stage part, no? Consolidation stage part. Okay. Then next we apply the deviator stress or the delta sigma sub D. D means deviator. Okay, so that's deviator stress. Okay, So the deviator stress on the specimen is increased slowly. That means you have slowly applied the load here. Okay, you have slowly applied the load. This one here, as well as this one here. Okay, we have slowly applied the load to the specimen. This one here. We slowly apply the load to the specimen. Okay, and then during the application of that load, the drainage connection is kept open. Okay, so where's that one? So we keep open the drainage here at the bottom. Okay. And so the slow rate. No? So since you apply the load very slow, okay, then the slow rate of the deviator stress application would allow complete dissipation of any pore water pressure that develop. Um, then as a result, the pore water pressure increase with respect to the deviator stress, that's u sub d, will then be equal to zero over time. Okay. Okay. So here we have just a diagram of the consolidated drain triaxial test. Okay, wherein here in figure A, you have the specimen under the chamber confining pressure. Okay, during the consolidation stage. Okay, so during the consolidation stage, you have only sigma sub 3 or the confining pressure acting on the soil sample because of the surrounding fluid, either water or glycerine. Okay, so here in figure B, you have here the deviator stress application. Okay, wherein aside from the confining pressure surrounding the soil, then you also have the vertical forces due to the deviator stress application, no? Due to the application of the vertical load, no? From the vertical loading ram. Okay. Okay. Now, because the pore water pressure developed during the test is completely dissipated because you have a drain test. No? You have a drain test condition. Okay, so pore water is completely dissipated. That means the soil has fully consolidated. Okay, okay. Considering our discussion last meeting, no, on consolidation process. Okay, so in this case, the total and the effective confining stress is equal, or sigma sub 3 is your total confining stress is just equal to the effective confining stress. Okay. While the total and the effective axial stress at failure, okay, is also the same. Okay. Sigma sub 1 and sigma sub 1 prime is the same for the consolidated drain test. Okay. Yeah. Because of the dissipation of the excess pore water pressure. Okay? Where sigma sub 1 or sigma sub 1 prime is equal to sigma sub 3 plus the deviator stress at failure. No? The increase in, or the change in the deviator stress at failure. Okay? So again, in the triaxial test, a sigma sub 1 prime is now what we call the major principal effective stress at failure, while a sigma sub 3 prime is what we call the minor principal effective stress at failure. Now, so this is now the um, major principal stress, okay, in this direction, and then you have here the minor principal stress in this direction. Okay. So here in this figure, we mm, we have the effective stress of failure envelope. Uh, in the case of a drain test, so again, when you say drain test, in triaxial test, we are referring to the consolidated drain test. So in this case, we have a result, a typical result for the case of a sand or a normally consolidated clay. Okay, yeah. Wherein here you have no cohesion, but you have the effective friction angle. Okay, so here we have your sigma sub 1. Okay, and then here you have your sigma sub 3, which is now sigma sub 1 is the major principal stress, and then sigma sub 3 is the minor principal stress. No, wherein the diameter or the difference between the two stresses, okay, is equal to the deviator stress, no? Or when you say sigma sub 1 minus sigma sub 3 is equal to the deviator stress at failure. Okay, so that means sigma sub 1 minus sigma sub 3 is equal to the deviator stress at failure. Okay, so if we conduct, say, two or more specimens, for example, usually three specimens, at least three specimens, then we can generate the failure envelope tangent to these specimens. Okay, or yeah, these more circles of these failed specimens. And then with that, with this failure envelope, then we can generate the effective friction angle. Okay. So with the determination of the effective friction angle, then most probably we can probably predict the failure plane angle with respect to the major principal plane. Okay, that's theta, which is equal to 45 plus the effective friction angle over 2. Okay. Okay. So here the effective friction angle can be determined by this formula here. For example, that's a sine of phi prime is equal to this AO prime over OO prime. No, or it's just basically this angle. Okay. Now, here you have seen the result for a normally consolidated clay. Now, in the case of an over-consolidated clay, then we have here this the form of the failure envelope, okay, which uh, wherein we now have a certain cohesion intercept, no? Or C prime. Okay, so this one here is the behavior for a normally consolidated clay. Okay, then at some point we have a break between the normally consolidated clay and the over consolidated clay. Okay, so for normally consolidated clay, you only have this effective stress failure envelope. But for an over consolidated clay, then you have this one for your effective stress failure envelope. Okay, wherein we now call this your sigma sub 1 prime. Okay, yeah. So depending whether you have an over consolidated or normally consolidated clay sample, for example, then either the effective equation can be zero or it can have a value. Okay. Okay. So next we have the consolidated undrained triaxial test. Okay. So in practice, the consolidated undrained triaxial test is the most common type of triaxial test. Okay, wherein we also do pore water pressure measurement. Okay. Now, in this test, the saturated soil specimen is first consolidated by an all-around chamber fluid pressure. That's your sigma sub 3. Okay. Um, um, that results in drainage. Okay. That results in drainage. So that means you have consolidation. Okay. So you have the dissipation of the excess pore water pressure. Okay. Now, after the pore water pressure generated by the application of the confining pressure is dissipated, okay, that's the consolidated stage. Okay, consolidated stage. Then we now apply the deviator stress. Okay, that's your delta sigma sub D. Okay, on the specimen, which is then continuously increased to cause failure. Okay, so you have these figures in your book. You can have a look at it. Okay, now during this phase of the test, no, during the application of the deviator stress, okay, stage, okay, the drainage line will then be kept closed. No? Okay, so you will close the drainage line. Okay. Now, because drainage is not permitted during the application of the deviator stress, then the pore water pressure in the soil sample will increase. And then we can now call that as delta U sub D. Now, this is your deviator stress. Okay. So that will increase. Okay. Because pore water pressure will not be dissipated. Now, during the test, okay, simultaneous measurements of the deviator stress, okay, and the pore water pressure increase caused by the deviator stress are measured, okay, yeah, and then with that we can then have or we can express no, the increase in the pore water pressure delta U sub D considering the Skempton's A pore pressure parameter. That's A bar. Okay, where A bar is equal to the pore water pressure increase due to the deviator stress, okay, over the increase in the deviator stress itself. Okay, yeah. Now, in literatures, you can have values for the B pore pressure parameter and the A pore pressure parameter for different types of soils. Okay, and this was discovered by Skempton in 1954. So, unlike the consolidated drain test, the total and the effective principal stresses are not the same, okay, in the consolidated undrained test. Now, because in the consolidated drain test or in the drain test, the total and effective principal stresses are the same. Okay, as if you try to recall here, okay, the total and the effective stresses are the same. Okay, but in the consolidated undrained test, the total and the effective stresses are not the same. Okay. So here, for example, the major principal stress at failure, or that's the for the total case, okay, for the total stress case, then that's equal to sigma sub 3 plus, or that's the confining pressure, sigma sub 3, plus the deviator stress at failure, okay, will now be equal to sigma sub 1, okay, yeah. So that's this one here. Now, if we go back, that's a sigma sub 3 plus the deviator stress is equal to sigma sub 1. Okay. While the major principal stress at failure for the effective case is equal to sigma sub 1 minus the increase in the pore water pressure due to the deviator stress at failure, okay, at failure is now equal to sigma sub 1 prime. Okay. Now, the minor principal stress at failure for the total stress behavior is equal to the confining pressure, which is sigma sub 3. Okay. While the minor principal stress at failure, or with respect to the effective case, or that's your sigma sub 3 prime, is now equal to sigma sub 3, which is the confining pressure in the chamber, minus the pore water pressure increase due to the deviator stress at failure. Okay. Now, if we subtract, okay, now if we subtract these two equations here, okay, if we subtract these two equations here, we can see that sigma sub 1 minus sigma sub 3 is just equal to sigma sub 1 prime minus sigma sub 3 prime. Okay? Because this one will be canceled out. Okay? So that means that this term here is just equal to this term, is just equal to the pore water pressure increase due to the deviator stress at failure. Okay? Yeah. Okay. So here we see an example result. Okay, an example result for a consolidated undrained triaxial test. Okay, a consolidated undrained triaxial test with pore pressure measurement. Okay, and so here we have done two test samples, for example, with their corresponding Moore column, with their Moore circles. Okay, and then we can plot the failure envelope. Okay, yeah. So here we have the failure envelope with respect to the total stress approach. Okay, total stress approach. Okay, wherein you only have the normal stress here. Okay, but if we consider now the effective stress behavior, wherein we subtract the increase in the pore water pressure due to the deviator stress at failure, okay, uh, between sigma sub 1 and sigma sub 1 prime, and then sigma sub 3 and sigma sub 3 prime, okay, that's actually this one here. No? Uh, so sigma sub 1 at the total minus the pore water pressure will give you the effective. So that actually gives you this line here. Okay. Yeah, this difference. Okay. So that means if we subtract the pore water pressure from the total stress parameters to arrive at the effective stress parameters, then these more circles will shift to the left in such a way that the failure envelope at these more circles will generate a phi prime value. Okay. And then here you can see that the phi prime or the effective friction angle is bigger or greater than the total stress friction angle. Okay. Here we expect the friction angle, the effective friction angle to be bigger because then here um, you don't have the pore water pressure anymore helping in the resistance of the loop. Okay, that's why we always better to have we always prefer to have the effective stress shear strength parameters over the total stress shear strength parameters. Okay? So even though while we have done here undrained testing, which is supposed to be total stress approach, but since we measured the pore water pressure, then for the CU test with pore water pressure measurement, we can still determine the effective stress parameters. No? Okay, the same as what we can derive from the consolidated drain test. Okay, yeah, which can take some time to do in the lab. Okay, um, okay. Now, now in the case of consolidated drain, okay, I hope you're seeing my cursor. In the case of the consolidated drain test, okay, on clay soils, this can take some considerable time. Okay, the same as what we have seen in the direct shear test. Okay, for drain direct shear test for clays. Um, for this reason, the consolidated undrained test or the CO test can be conducted on such soils with poor pressure measurement also to obtain the drained shear strength parameters. Okay. So since drainage is not allowed in this test during the application of the deviator stress, then they can be performed quickly. Okay. During the test. Okay. So that's why it would be good to measure the pore water pressure, okay, increase during the consolidated undrained test. Okay. Okay. So the last one is the unconsolidated undrained triaxial test, or we call it the UU test, no, in practice, no. Okay, UU test. So in the unconsolidated undrained test, okay, drainage from the soil specimen is not permitted during the application of the chamber or the cell pressure sigma sub 3. So that means that there is no dissipation of pore water pressure. So that means there is no consolidation on the specimen. So that's why we call it unconsolidated. Okay. And then the test specimen is sheared to failure by the application of the deviator stress, or that's the delta sigma sub d. Okay, that's your actually your sigma sub 1 minus sigma sub 3, but still the drainage is still prevented. Okay, so during the application of the cell pressure as well as the application of the deviator stress or the application of the load, at these stages the drainage is being closed. Okay, now, since drainage is not allowed at any stage, then the test can be performed quickly. Okay. Um, so, because of the application of the chamber confining pressure, sigma sub 3, the pore water pressure in the soil specimen will increase by U sub C. Okay. Yeah. And then a further increase in the pore water pressure will occur because of the deviator stress application, or just the application of the load. Okay. So therefore, the total pore water pressure U in the specimen at any stage of deviator stress application will then be given by this equation here. Okay. Wherein the total pore water pressure U is equal to the pore water pressure increase during the application of the confining pressure. And then you also have the pore water pressure increase upon the application of the deviator stress. Okay. So I think earlier we can relate the pore water pressure increase due to the confining pressure to be equal to the B pore pressure parameter multiplied by the confining pressure sigma sub 3, and then the increase in the pore water pressure due to the deviator stress can be equal to the A pore pressure parameter multiplied by the deviator stress increase. Okay. So then just combine, just substitute this one here. Then we can get this equation here for the total pore water pressure U. Okay. Now, this test, which is usually the UU test, is usually conducted on clay specimens, okay, because it can be done quite fast. Um, depends on a very important stress strength concept for cohesive soils. Okay, if the soil is fully saturated. Okay, now the added axial stress at failure. Okay, so in the UU test, the added axial stress at failure or delta sigma sub d at failure is practically the same regardless of the chamber confining pressure. Okay. So, for example, this one here. This is a result of a UU triaxial test on a fully saturated cohesive soil. Okay. So here, since we are doing an undrained test, so the UU test is also what we call the undrained test. Okay. So here we see that whatever is the value of the confining pressure, may it be this one here, or you increase the confining pressure to this value or this value, we can see that the more circles, okay, are just the same. Okay, yeah, which means that the deviator stress is the same. Okay, that's what this means. Okay, the deviator stress is just the same. Okay, so then in that case, you can have a horizontal failure envelope being or having the friction angle equal to zero. Okay, and this is just equal to a total stress approach. Okay, total stress approach. Okay, because we have undrained conditions. So that means the poor water pressure is helping in resisting the load. Okay, so that means that behavior now is what we call a phi equal to zero condition. Okay, so that one, phi equal to zero condition. You have a horizontal failure envelope. Okay, so with phi equal to zero, okay, then the shear stress or the shear strength at failure, if phi is equal to zero, is just equal to C or the equation. So in this case, we call the equation to be C sub u, okay? C sub u, which is now defined as the undrained shear strength. No? If you do a UU triaxial test or the unconsolidated undrained test, okay, which is just equal to the CU is just equal to the radius. No? The CU is just equal to the radius of the Moore circles. This one here. Okay. Um, Now in American codes, just try not to be confused. Just in case you can read American codes, or because sometimes they use S sub U. Okay, so C sub U or S sub U is just the same. No? That's the undrained shear strength. Okay. Now just a note here that the phi equal to zero concept is only applicable to saturated clays and silts. Okay. Okay. Now, here we now have the unconfined. Okay, the unconfined compression test. Okay, is a special type of a UU test that is commonly used for clay specimens. Okay. Now, in this test, the confining pressure sigma sub three. Okay, is zero because there's no confining pressure. Okay, there's no chamber here. Okay, for example, this figure here. Okay. So there is no. This is an example of an unconfined compression test, where there's no chamber. No, there's no chamber, so the soil is just exposed outside. So there is no confining pressure. Okay, so that means a sigma sub three is zero. Okay, then an actual load is rapidly applied to the specimen to cause failure. Okay. So at failure, the total minor principal stress is zero. Okay, because there's no confining pressure. While the total major principal stress is sigma sub 1. Okay, so as shown here. Okay, so there is no sigma sub 3, that's 0, but you have sigma sub 1. Okay, because that's this one, no? Created by this load, the sigma sub 1. And then there's no chamber, there's no confining pressure, so sigma sub 3 is 0. Okay, now since the undrained shear strength, okay, or the CU or the S sub U is independent of the confining pressure. Okay. As long as the soil is fully saturated and fully undrained. No? So that means here we saturate the samples. Okay. Then the shear strength at failure, okay, will then be equal to sigma sub 1 over 2, or that will be equal to QU over 2. Okay. Where QU over 2 is now equal to your C sub U. Where Q sub U here is now what you call your unconfined compression strength derived from the unconfined compression test. Okay, and then QU over 2 is now equal to the undrained shear strength derived with the unconsolidated undrained test. Okay, so CU, the undrained shear strength, can be derived by the UU test. And then QU, which is the unconfined compression test strength, rather, can be derived by the unconfined compression test. And this is the relationship between the two. Okay. So where this sigma sub 1 here is now your QU. Okay. So that means the failure envelope will look like this, still horizontal, where phi is equal to 0. But since sigma sub 3 is 0, so that means the Moore circle will start from here. Sigma sub 3 equal to 0. And then this point here will now be your sigma sub 1, okay, which is now equal to your unconfined compression strength. Okay, so that means your QU is your diameter. Your diameter. So the diameter, if you divide that by 2, then that will give you the radius, which is now your undrained, equivalent to your undrained shear strength. Okay, C sub U. Yeah. So here we have the general relationship between the consistency of clays and the unconfined compression strength of clays. No? Okay, so again, in the field, we can determine the consistency of clays, whether we have very soft, medium stiff or firm, then stiff, very stiff, and hard clays. And then depending on the consistency of clays, you can have here different values for the unconfined compression strength. Okay. So for example, if you have a very stiff clay with a QU with an unconfined compression strength of 400 kilopascals, then according to this formula here, the undrained shear strength can probably be equal to 200 no, kilopascals. Okay. In geotechnical analysis, normally we use the undrained shear strength, no? Not the unconfined compression strength. Okay. We either do it in the lab or we can have established empirical relationships. Okay. Okay, so here we have examples of soil samples, okay, tested under an unconfined compression test equipment. So this one here is an example of a failure by shear. So you have here this is now your basically your failure plane, okay. So it is roughly 90 degrees plus, or that's roughly 45 degrees, no? That's roughly 45. So if this is your horizontal plane, this is for your 45 degrees plus, yeah, this one is more than 45 degrees. So that's 45 degrees plus 5 prime over 2. Okay, so this is now the failure plane. So this is the failure by shear, and this one here is a failure by bulging. No, okay. The sample didn't fail by shear, but it failed by bulging. Okay. Okay. Now, with respect to the testing of clays, no, we need to understand that some clays are sensitive clays. Okay, so let's be careful with sensitive clays. Okay, now what we mean by sensitivity. Okay, so for many naturally deposited clay soils, the unconfined compression strength is reduced greatly when the soils are tested after remolding. Okay, sometimes you can remold, no? Remold the clays for testing without any change in the moisture content. Okay, so if the strength is reduced, no, after remolding, then this property of clay soils is what we call now as sensitivity. Okay, wherein the sensitivity is now defined as the undrained shear strength over undrained shear strength of the undisturbed clay sample over the undrained shear strength of a remolded sample. Okay. Now, the sensitivity ratio of most clays ranges from about 1 to 8. However, for highly flocculent marine clay deposits, I think way before we describe what we mean by flocculent structure. Okay. So for highly flocculent marine clay deposits, can have sensitivity ratios ranging from 10 to 80. Okay. And then some clays would turn into viscous fluids. Okay. So in these quick clays, no, we call them quick clays. Um, these clays would turn into viscous fluids upon remolding. Okay. So these quick clays are mostly found in the previously glaciated areas of North America and Scandinavia, for example. Okay. So here in your book, you can just have some different values for the sensitivity and their descriptions. No? Okay. So 1 to 8 is the normal range for this between insensitive to very sensitive. Okay. And then you have here your quick lace, no? From 10 to around 80. No? The quick lace. Okay. Now, in the field, no? Okay. So far we have discussed the laboratory tests to determine the shear strength parameters of soils. Um, if you don't have any lab equipment nearby, sometimes what you can do in the field is you can do some field equipments. No? You can do some in situ test. One of these is the vein shear test. Okay, wherein several empirical relationships have been proposed between the undrained shear strength and the effective overburden pressure. Okay, the effective overburden pressure, which we have been discussing in the previous lectures. Okay, and then the most commonly cited relationship is the one given by Skempton, as given in equation 12.35 in your book. Okay, so that's this one here, which is the undrained shear strength based from a vein shear test over the effective overburden pressure, sigma sub O prime is equal to this one here with respect to the plasticity index. Okay, but this is only applicable for a normally consolidated clay. Okay. Now, this guy in 1974 showed that as the plasticity of the source increases, the undrained shear strength obtained from vein shear tests done in the field may give results that are unsafe for foundation design. That means it gives gives a quite high value. Okay, it gives a quite high value. For this reason, this guy suggested a certain correction factor lambda, which is given by this one here, to be applied to the undrained shear strength derived from vein shear test to be used in the design. Okay. Yeah. Okay. So this one here is a typical example of a vein shear test equipment. Okay. It has a rotator, no, which you insert into the ground and then you try to rotate. Okay. Yeah. And then this one here is a pocket penetrometer, which can also determine the undrained shear strength of a soil sample. Okay. Which you can also do in the field. No? We call it a pocket penetrometer. Okay. So I think these are the discussions, the theory behind, the basic theory, at least the basic theory behind the shear strength of soils. Okay. So just to have one example here, I think for the rest of the examples, my colleagues can provide them to you. Okay, so let me just give you one example. Okay. So here we have a soil profile provided here, wherein you have here you have 3 meters of dry sand. Okay, then with that you have the groundwater level. Okay, so below it are all saturated. Okay, so you have here a saturated clay with a water content of 30% and a specific gravity of 2.68 for clay. And then the dry unit weight, or sorry, um, the the unit weight of the sand, okay, of the dry sand is 15.5 kilonewtons per cubic meter. Okay, so the then the bottom of the clay layer is about 24 meters from ground surface. Then after that, you have some rock. Okay. Yeah. So the clay is normally consolidated. Okay. Then the liquid limit and the plastic limit is provided. So in this problem, we are just asked to estimate, for example, the unconfined compression strength of the clay at a depth of 10 meters measured from ground surface. So let's say at this point, no, we are asked to measure the unconfined compression strength at this point. Okay. Um, so, of course, in the field, if you like, you can excavate until 10 meters and then you can do some vein shear test, or if you can do some pocket penetrometer test. No? Although it's a bit difficult to excavate until 10 meters, no, without shoring. Okay. So for this problem, we are asked to use the Skempton's relationship as a given here. Okay. For example, since we have a normally consolidated clay. No? So so in using this formula, we okay, we uh, since we are after for the let's see, where's that? We're after for the unconfined compression strength. Okay. We are after for the unconfined compression strength. So if we want to get this, then this is just equal to 2 times the undrained shear strength. But the undrained shear strength using a vane shear can be provided by this one. Okay. But using this formula, we need to determine the effective overburden stress. Okay. At 10-meter depth. Okay. At 10-meter depth. So to do that, we have the unit weight of sand that is a given here. Sorry, that is given. But for the unit weight of clay, we need to derive that. Okay. So since the clay is saturated, then we need to determine the effective, not the effective unit weight of clay. Okay. So for the effective unit weight of clay, we can have this formula here, okay, which you can just try to check in, I think in the first two, three lectures we have some equations for this one, different equations for unit weight. You can just try to scan through, okay. So if you want to use this formula, then we need the void ratio, okay. Now, for the void ratio, we have the popular formula SE equal to WGS, where S is the degree of saturation, E is the void ratio, W is the water content, and then GS is the specific gravity. Okay. So the water content and the specific gravity is given. That's 30%. So that's zero point 0.3 water content. Now, the degree of saturation can be treated as 1 since you have a saturated clay layer. So the degree of saturation is 100% for a fully saturated condition. So then here we can derive the void ratio equal to zero point 0.8. Substitute it here in this formula. You have the specific gravity and, yeah, the unit weight of water, which is 9.81. Okay, so then we can get the effective unit weight of the clay. So to determine now the effective stress at a depth of 10 meters below the ground surface, so um, we now have 3 meters times the unit weight of the dry sand plus this is if this is 10, that's 3, so this is 7 meters of clay. 7 meters of clay um, multiplied by the effective unit weight. Okay, the effective unit weight of clay, this one here, which is 9.16. Okay, so just calculate this one, then we can now determine the effective overburden stress. Okay, yeah. So with that, just substitute it here in the formula. Okay, and then the plasticity index is equal to the liquid limit minus the plastic limit. Okay, that's this one here. So then we can get the value now of the undrained shear strength based on the vane shear test, okay, that you have conducted in the field, okay. And then, yeah, just apply some corrections here for the lambda um, um, to get the undrained shear strength to be used for design. Okay, so we have reduced it from 26 to 23, for example. Okay. And then from there, we can just apply this to get the formula for the undrained shear strength. Unconfined rather, unconfined compression strength, which is now equal to 2 times the undrained shear strength. Okay, so that gives you about 46 kilopascals. Okay. Yeah. So we have determined the unconfined compression strength based on the field. Or what you can do, if you can reach this depth, get a sample here, bring it to the lab, and then have it tested with an unconfined compression test. And hopefully we will get this, hopefully we get the same results. Okay. Okay. So yeah, I think that's the end of my presentation. Okay. So do you have any questions or clarifications so far? I think we're just on time. We still have about 10 minutes for questions or some if you have some any clarifications. Okay, let me just stop share so I can see everyone. Um, so do you have any questions or clarifications so far? So again, just to summarize, for the triaxial test, we have um, the three types of tests. No? The CD test or the drain test, the CU test with poor water pressure measurement, and then the undrained test or the UU test. No? And then we also have the unconfined compression test as well as the direct shear test to determine the shear strength parameters of the soil. Okay. So I'm not sure if you will be performing this in the lab as well. So again, don't worry, all of these things can just be found in your book. Okay. So any questions or clarification so far? Maybe there's something you want to clarify. Just checking at the chat box. I guess there's no question. Okay. Okay. So I just hope I am clear with everyone. Okay. Um, okay. So if there are no questions so far, okay. So yeah. So thank you everyone for your time. Okay. And have a pleasant evening. Okay. Thank you everyone.